All right, so Daniel Kahneman's got this book, Thinking Fast and Slow, right? He's got System 1 thinking, which is this whip snap response. When I say, what is the capital of Massachusetts? You'd say Boston, right? That's how essentially the relationship with co-pilots are operated today. He also has this other concept of System 2 thinking, right? Which is very deep, very logical, something that maybe you would use for solving a physics problem, a calculus problem, a hard programming problem potentially. And it involves methodical thought process, sometimes for seconds, sometimes for minutes, sometimes for hours. And so we've seen OpenAI come out with O1, right? Which is the first precipice of System 2 AI, which thinks for 20 seconds on average and gives a much, much higher response. So before we talk about that, first help us figure out how to define it. It's like, what is this System 2 AI concept?
I think System 2 AI is a new frontier in models where you had, and I would define that frontier as reasoning. You have your typical chatbots, agents, or whatever you'd like to call it, that are designed, they're still operating on the same paradigm, which is you give it their input, they're completing the response token by token, right? They're figuring out the next best set of tokens to use to complete the response. That's how the transformer architecture works. But now, if you go with that strategy, then what happens is there are inherent flaws in the transformer architecture that lead to problems. And the best example that OpenAI has pioneered and has solved successfully is the number of R's in the word strawberry, right? We saw that every single LLM out there, out of the box, that is transformer-based, struggles with that concept. We know that there are liquid foundation models now with liquid AI, but even they cannot get that right because of how fundamentally different the technology works.
In their defense, I don't think I can get it right most times.
Yeah, of course.
But if I use my System 2 thinking.
Yes, that's exactly. It's a hard problem with System 1 for these models. But the way to think about System 2 is, in the classic terms of how it was actually used and defined, it's not what you have top of mind, but it's what you've thought through and validated and reasoned through, if you will, to come up with an answer that you are more confident about. And that's essentially what OpenAI is doing, is instead of giving you the answer that best fits your query, let's spend some time on it. Let's break down let's formalize the approach that you would use to answer the question. And let's spend 20 seconds or however long it takes for processing that. They've defined a new category of tokens that they're calling, reasoning tokens. And you don't have access to those tokens that OpenAI uses, because if, in OpenAI's words, if you had access to them, you could figure out what they're doing and build a system yourself. So the point really is that, yes, it's a different model, but the focus needs to be on the fact that it's a different process that you can achieve with traditional models.
And so really OpenAI is quite scarce about what is happening in that 20 seconds. For them, I think there's really deep IP there that they're trying to protect. So talk about the techniques that are used in System 2 AI to get better results.
Yes.
We're sort of speculating on O1, but we build System 2 AI all day, so we're not speculating on what we use.
Of course. So an easy way to think about System 2 is, what if you had this system where you have maybe more than one LLM, if you were using a standard LLM process, or LLM with some assistance with other kinds of models, where you had a system prompt that whenever you have an input, you would think about it, come up with steps, and then formalize your approach, right, before you answered the question, right? And when you do that, you would, come up and hopefully work out a process that actually is effective at solving the problem. Like, for example, I mentioned this in one of the earlier Blitzy bites. You could get the specific problem, counting the number of R's in strawberry, solved by any LLM out there if you simply asked it to write code to answer every single question, right? So whenever you get a question, you're not going to answer that. You're going to write code that solves for that, and then you're going to render the output. You can do that in Claude artifacts, for example, right? So when you take that approach, now the model is using, time, and it's coming up with it's using a solution it built to answer your question. So that's not reasoning per se, but it is following a structured approach to answering that problem. Now, in terms of techniques, there have been a lot of discussions, and there's been a lot of progress in reasoning-based AI. Some of the most popular ones have been chain of thought, tree of thought, and there's a bunch of other variations of that based on the specific problem that you're trying to solve. But the gist of it and what's been most effective is, given a prompt, plan your approach and dedicate tokens to this thinking process. So, the LLM's goal is to use its tokens effectively to answer the query. But instead of that, you're going to change the paradigm. You're going to spend time coming up with the approach, planning it, and then executing based on your plan. And the hope is that within that process, you've come up with a framework that helps you address the problem more effectively. And if you think about how humans think when addressing the complex problems like math or anything else that requires a rule set and that has theorems or fundamental principles and laws that you cannot break, you would need a framework to address them. You would need steps. And that is why reasoning-based AI and System 2 AI is effective at getting higher quality results and outputs.
Dramatically higher
Yes,
quality, right? And so I think folks would be interested to understand from a breakdown perspective, there's a planning process and there's an execution process of providing the output. So maybe you can talk a bit about what that looks like for us as an example of a System 2 AI company, and whether that maps onto other categories, we'll find out.
Yes.
I don't know if anyone's built as large of a System 2 AI system as we have.
Yes.
But yeah, talk a bit about how our breakdown is for that.
Yeah, so it's super interesting what we're doing. We're always operating in the bounds of software, and we're working with a fundamental document, which is the technical specification, which is the architect's design of what a software project should do. There are a lot of projects that can fit into that definition, that can work with a single document, and that could be fit into a single GitHub repo.
Architecture, CAD, maybe chemical process.
Yes.
I'm pushing my chemistry classes back in the day, but yeah, I mean, it's a 15-pager on our end, which is pretty substantive, and that's really how a lot of huge projects will get sort of started with a source of truth.
Yes, you can fit a complete project. You can get the gist of the complete project in a 15-page document.
Yeah.
If you're really good at it, you could do it with fewer pages.
Yeah.
But I think 15 to 20 pages is a good starting point to define a project with at a high level with complex features. And then you can have a document for every single feature, right? And then if it's a really complex project, you may have up to 50 such documents, and that's completely fine. You may have 50 repos, and you may have a solution that integrates all of those. So enterprises do all of this on a day-to-day basis, right? It's a format that's tried and tested, and that works. But the challenge really for AI is that, one, if you have 50 such documents, even though it may fit in some of the most advanced models, like the Gemini has a 1 million context window, 1 million-ish. The ish is the critical bit. So we've seen, even if you use Claude 3.5 Sonnet, which is highly regarded as one of the best coding models out there, and we definitely agree, if you push its limits in terms of the input context window, it struggles to follow all of your instructions. And that's not me blaming Claude for poor model quality. It affects every other model out there. It's not just speaking about on Anthropic. But it's a challenge now. The limits that are quoted by model providers are the theoretical maximum, and they may not be realized practically in every single run. So the challenge for you with a large tech spec or a collection of large technical specifications is, how do you get the model to understand all of that information? And given that you are able to get it to understand, then how do you get it to generate outputs that match that scale, right? So we've mapped one technical specification to about 100,000 to 150,000 lines of code, right? So if you have 50 features at 50 times 150K, that's how many lines of code would be in your platform, in your product, right? So when you have outputs at that scale, clearly with the existing models out there that have the output length of 8,000 tokens and that struggle beyond writing 1,000 lines of code, you're definitely not going to get anywhere close to 150,000 lines. Or even if you get close to, let's say, 1,000 or 2,000 lines of code after many iterations, there are going to be issues that you need to fix. And it's virtually unthinkable for someone to use a model like this and solo build, a 150,000 line repo that actually solves for what the original requirement was. And that's essentially the problem we've solved with our solution, with our inventions. So we have pioneered the ability to dynamically recruit AI agents to solve problems. So for example, if your technical specification is 20 pages long and it has a number of complex features that requires maybe about 700 files in a GitHub repository to solve completely, right? Then we'll recruit an appropriate number of agents that is best suited to solve that problem based on our proprietary algorithm that recruits and assigns agents based on the size of the context window that they would use and the length of the output that they would be expected to produce, right?
And the type of task that they're expected to execute.
And the type of task that they're expected to execute. Thank you for that. So when you have a specialized system that can do that, you can ensure that every model operates in its most optimal range. And the algorithm is different for 3.5 Sonnet versus GPT-4o versus O1, right? Because they all have different operating paradigms. Like for example, the O1 models as of date don't even support a system message. You can only use human messages, and they don't support tool calling. So there are a lot of challenges that go into making these considerations, and there are shifting limits. The 200K token limit applies today, but it may not be the same tomorrow, right? So there's a constant development overhead into making sure that the system is always at pace with the improvements on the model provider's end. Claude recently came out with a new model, for example, of a new version of Sonnet that did better than the previous one, even when you push it to its limits. So it's a continuous process. And the way like I said, we recruit these agents dynamically. We always operate in the optimum window for that particular model. And we recruit just the right amount of agents to write code, but we don't jump to writing code.
Yep.
So here's where the magic happens. We think about solving each requirement at a macro level. So every AI agent is recruiting the right AI agent that it can delegate to for a particular process, right? So for example, if it's a front-end use case, then we have agents that have specialized instructions for React that are based on our learnings and observations that work best in that ecosystem. We have some default choices. We also support whatever preferences the enterprise have. Like for example, some firms want to use Next.js with React. Some others prefer React and Tailwind with White. So there's a large variety of options out there. Every ecosystem has one right set of choices. So it's a really, really hard problem to solve right. Like if you just want a model to spit out code, you can do that, but it's not going to be any good because the humans are going to have to spend a ton of time making it work. And it's not always possible to make it work, right? Because when you're dealing with such large code bases, chances are there's circular dependencies riddled in there. And a circular dependency.
Now with Blitzy, but yeah.
No, not with Blitzy, of course. But when you have circular dependencies, it's really hard to break those linkages because the model has come up with a set of assumptions. And if you change those assumptions, the output is practically useless, right? So it was a bunch of there were a bunch of like really hard inventing processes on our end that led to solving those problems. But that's essentially what we do. We think about all of the requirements. We think about how do we solve everything, make sure we don't miss anything. How do we address the constraints that the firm has set with us? Like for example, I wanted to follow the specific PEP style guide for Python, or I wanted to retain whatever existing best practices we followed in the code so that the code feels familiar to me when I go read that, right? If I have code that's written using one style in one part of the application, and then another part uses a completely different style, it's hard on me as a developer to understand what the new code does, right? So we solve for all of those nuances by thinking about it. And every agent helps every other agent by delegating tasks, by bringing in the task that the agent that has the right instructions or access to the right set of tools to decide which file gets worked on next, which module or which function gets written next. And it's a coordinative process across thousands of agents. We've seen at times, we've had jobs with 3,000 plus agents for 150,000 plus lines of code. And it's a dynamic process. It's not always deterministic how many agents will be there. It completely depends on the complexity of the problem. But once we've gone through that thinking process, we go through code generation. And then even after code generation, we have a process where we validate all of the code that's generated before the humans see it, right? So after going through this process, that could take anywhere from like 4 hours to 12 hours. And we are thinking for that process, right? Because we are laying down the groundwork, we're assigning things to the right agents. We are quite often working with the intermediate outputs and changing them to make sure that there are no circular dependencies, to make sure that we're using the right packages, that they're not deprecated or that they're not incompatible.
And by we, you mean some Archie architectural agents,
yes,
right? Like that, not we.
Yeah, I've spent so much time with these agents. Like now they're like
part of our team.
Yes.
Yeah. They're like, how big are you guys? I'm like, we're either 20 or 3,000, depending on
Exactly. Yeah. Like I feel like one of them now. It's like we're deep, man. But after we've gone through that process, that's when we have the code, and that's the output that the humans can now work with, right? So it's a high quality output. You don't have to spend hours taking it back to the AI and getting it redone before you have something that's usable. It's something that follows your tech spec. That's our gold standard in building software, and that's what enterprise use today. So you're not getting used to this new mindset of how do I work with these AI models and get it to understand what I'm saying.
Yeah, I think that's right. I think there's some macro lessons around System 2 AI that abstract to other domains, which I think are really interesting to consider. And so I think some insights that are, I think, shareable external are, we think of our System 2 AI platform as essentially an organization, right? And it's like, this is an organization. This organization's goal is to build software. If we were to build software without agents, here is all of the skill sets that we would need. And then what is the max capacity or skill set of an individual agent? It's a thin slice of what you could ever expect a human to do, but we can have as many of these things as we want, right? Yes. And so it's like, instead of maybe one front-end engineer, you might have dozens of different agents that can come up with the same skill set as that front engineer that can work at the speed of compute, right? And so that's generally how we think about solving for which agents to have within the system, within the org for us. And then the problem to be solved is, how do you want those agents to coordinate? But you can really go back to like, if you were to compress the human jobs to be done into an infinite repeatable parallel series, then what would that look like? And that is what you were trying to achieve agentically, right?
Yes. So it's all about, if you think about how humans solve problems, they look at a problem, they try to break it down into subtasks, and they prioritize the tasks, right? And quite often there are points where the outcome of a particular task influences the next subset of tasks. So you have a decision tree, right? And you traverse each path based on the outcome of that task. So we've found a way to normalize that and incorporate it into our platform. So we've tried to mimic the human software development process. And because we're doing that, and because we're working with patterns and paradigms that have been perfected by humans over many years that software has existed, the final output is something that humans find easy to comprehend and to absorb and to use in their workflows, as opposed to if you were to let the AI do its job and not monitor it completely, you would get an output that feels alien. Mm-hmm. So that's actually where the tension is coming from in the AI products of today, where the AI spits out code and or produces outputs that humans are not familiar with. And that's a hard problem that we have deliberately solved with this platform.
Yeah, I think chain of thought has been a bit, it's too simple to solve some of these problems. It's fine in hyper-deterministic scenarios, but you really have to be able to delete some of your work in the process, just like a human deletes some of their work in their process. And so you plan, you build, you delete, and by we, the agents plan, the agents build, the agents delete, the agents build, the agents delete, the agents build. And so by having a system that is flexible in this nature, that is iteratively working towards the right outcome, which ultimately is the tech spec in something that can compile, then we can sort of get there within that time window. I think we have a unique advantage in code because code compiles, right? And so there is a source of truth that you can work towards that is accurate to represent the outcome. It doesn't mean it's going to compile and be perfect against the tech spec, but it is sort of ridden of errors, and you can sort of get to perfection on the tech spec other ways throughout. And so how should folks think about what the best domains are to go really big on System 2 AI?
I think you've underscored a really important point in what you said there, which is code can be compiled. So you do have a final answer that tells you whether you solved the problem or not, right? Now, when you talk about code compiling, there's also requirements that may be hard to validate qualitatively, right? Because they have to be validated qualitatively, and you cannot quantitatively validate them. But there is a way for humans to look at the output and to say if it addresses their requirements or not. And code is one of those domains that is therefore deterministic. Like if you can create validators that tell the humans if their requirement was solved or not, you can decide if your system solved the problem or not. And essentially the challenge there that we're solving is how do you build all those validators, and how do you give the humans confidence that their requirement was solved, and if not, what are the gaps and how do you close them? So coding is one such domain that is very valuable with System 2 AI because you can predict the output and evaluate it. I think there are a lot of other outputs and other domains where this is useful, especially if you can come up with a framework that can evaluate the quality of the output that is not necessarily qualitative. Then it can be super valuable. Like one example I can think about is maybe a design specification of a chip, right? I think this is one of the most valuable areas that System 2 AI and AI in general.
I was going to say accounting, but yours is so much better. That is so much more valuable.
It is. It's like Y Combinator recently said, hey, if you have any models that work on chip design, please come to us. Jensen recently announced that the most valuable frontier for NVIDIA to focus its AI manpower on is on chip design because it's a bottleneck. It's a really hard problem. And my background being in electrical engineering, chips are circuits, right? And you can either have a circuit that works correctly and that lets current flow from the input to the output, or you can mess that up completely and create short circuits and all kinds of problems and burn your chip, right? So because that's a deterministic problem, that's a great place to apply AI. But of course, you can also apply it to accounting, you can apply it to marketing, you can apply it to so many other places where you can measure the output and know that your AI is doing well.
I recently heard Sam Altman say, one, that he greatly dislikes people trying to compare generative AI to a previous technology as like, oh, it's just the PC, it's just the internet, it's just electricity. But if he had to, he would compare it to the transistor, which I thought was very interesting. So he very much has a view of the world that, someone asked him like, oh, Anthropic's like ahead of you guys in coding. And he's just like, you guys are not living where the ball is going, right? Saying like, these are just like the transistors. They're going to power these systems that fundamentally change the world. And we don't talk about the different types of transistors in a system, but they're in everything, right? And just like LLMs will be in everything, powering what we believe to be System 2 AI, that they have fundamentally different and varied and very powerful capabilities.
Well, if you think back to the transistor, right, then it was a fundamental moment of time when the transistor was invented and when it was actually deployed to the chips. Because we had, Moore's law, and Intel benefited from Moore's law for a very long time, where it said that the number of transistors on any chip will double every single year, and the cost will go down. Right. And that, if you think about what's happening today with AI, it's going to get easier and easier to get multiple agents. If you think of the transistor as the LLM, it's going to get easier to get multiple agents to coordinate just because we have, frameworks, we have multi-agent AI, there are software optimizations that make it easier. We were able to build this and solve for this. And there are going to be others that also ride on this wave. And the cost is going to go down. And that makes sense because we now have, smaller models. We have CPUs for inference that hopefully get solved. NVIDIA is pushing the frontier, building new chips that are more power efficient, that are cheaper to run. So the cost of inference is certainly going to go down. And which is why the analogy of the LLM to the transistor makes sense, because every other year, we're going to see more and more AI agents, and they're going to operate at a fraction of the cost and hopefully at a fraction of the power use as well.
And he also said, as he thought about path to AGI or ASI, he sort of broke it down into 5 levels. I think he took some inspiration from Tesla on the self-driving there, even though he wouldn't admit it, I'm sure. And he really says we're in level 2 right now, which is reasoning, which he sort of claims O1 is dominating, but he puts level 3 as true agentic behavior, meaning I can sort of give a model a task and go away and it'll solve it for some time. And so he's sort of describing level 3 as actual agentic capabilities. And so I would describe Blitzy as a vertical agentic capability, thousands of agents in this case cooperating together, reasoning as a part of that. And so do you think that we are at level 3 on the path to Sam Altman's level 5 to AGI?
I think it depends on how you would define it. Sam Altman has like a framework. Everyone likes to use different frameworks, but how I would define Blitzy is, yes, we're doing reasoning, but our path to generating output is also not deterministic. It is dynamic, right? So it completely depends on what the input is. We have a deterministic way to validate if we got to the output or not. So I would describe it as agentic. I think the fundamental path to AGI is about, you can give Blitzy a prompt about a known language that exists, that models have seen, right? Like Fortran, even though it's old, it has existed for a while. The models have seen it. C++, again, it's a new thing. But you cannot go to Blitzy and give it a new language that you invented and expect Blitzy to generate code reliably with that language. We'll try, the agents will try. But it's not going to be good because we don't know how to compile your language. You probably cannot fit a compiler definition in your input prompt because that would be way too big for us to understand. If it is a sophisticated language and not a ripoff of something, it's impossible for you to even define and explain the compiler, right? And to fit it on paper. So AGI is a world where AI agents and LLMs can learn new skills. They can take a language like that, learn how to build it, and be great at building programs with that language. Where the AI of today will use skills that they have learned, and this is all quoted, by the way, skills that they have learned from patterns. They will use pattern recognition to solve a new problem, but they will never get the skill of solving that problem unless you fine-tune that agent on that new problem. So that's the fundamental difference between where we are today and where we are hoping to be. But I think the winners in this race, be it OpenAI, Anthropic, anyone that's building on this platform, are those that rely on the giants for model updates. And that I think is a strategy that we're following that differentiates us from some of our potential competitors out there that have set out to build their own models. There is definitely nuances to this problem. And so there are definitely advantages in having your own models. But the disadvantage is that the existing model providers are definitely going to get better at code generation. And the problem is that the code generation is not very different from language because coding languages were built by humans. And so they're English adjacent, if not very close to English, like Python. So because...
That's why I like it.
Yeah, exactly. So as long as that's going to be true, which is most likely forever, in case of at least Python and C++ and all of those backbones, like C has been around forever. Like you cannot get rid of C no matter how much you hate it, right? It always shows up in some or the other form. And that's always going to be the case because those existing systems are based on those languages, right? So as long as that is the case, the models that are good at English are also going to be good enough at code. If those models have problems, the solution exists elsewhere, right? You can do validation, you can do all kinds of stuff to get high quality code. But an example where AGI would change things is if the LLMs or agents can come up with their own programming language that is much better than maybe even C at being memory efficient, at getting things done effectively, maybe without introducing as many bugs, and that fits with the current architecture of that time. I don't know if that will be transformed. I don't think so. But AGI-based systems can definitely come up with that.
That'll be a wild world. Until then, I think we think the winning strategy is use the proprietary models, fine-tune when you have to, when it really makes sense for specialization, and build really, really smart systems. So it's a fun one, man.
Yes.